Welcome to Multivariable Calculus lesson number 2, and again we're starting off with some single variable topics that were omitted from the BC curriculum. Today's lesson is on surface area. Let's review a little bit about volumes. Remember that when we rotated a curve, or a region rather, around the x-axis, we started off by approximating with cylinders whose widths were delta x, and so the volume of the cylinder here is pi r squared delta x. And in this case, since we're rotating around the x-axis, the radius is f of x. So we get pi times f of x squared delta x for each cylinder. Then as we let delta x go to dx, the instantaneous change along the x-axis, and the number of cylinders go to infinitely many, we end up with the integral from a to b, pi f of x squared dx, which gives us the exact volume when we rotate a curve around the x-axis. Okay, so here's a curve, and there's the image across the x-axis. So we're going to rotate the curve around the x-axis. And there's a picture of some circles that go around the surface. And you might think that, well, let's just do the same thing we did for volume. Let's take a little paper strip and make it delta x wide. And then the area of that strip then would be the circumference of the paper strip times delta x. And that would morph into the integral of the circumference times dx, and the circumference is 2 pi f of x because the radius of the paper strip is f of x. But that in fact doesn't work, and I'm going to show you why. So the question is, why isn't the surface area the integral from a to b of the circumference times dx, which equals the integral from a to b of 2 pi f of x dx? Well, the integral from a to b of 2 pi f of x dx can be written with the 2 pi in the front, and so that would be 2 pi times the area of the region bounded by the curve in the x-axis. Can that always be true? Will the surface area always be 2 pi times the area of the region? Well, here's an example where it actually is. F of x equals 1, and we're going to use the area from 0 to 2, and then revolve that around the x-axis and look at the surface area. So the area is 2, and the surface area is, it's just a cylinder, so the surface area is 2 pi r h, and it's on its side, so r is 1 and h is 2. That makes the surface area 4 pi, which is in fact 2 pi times the area of the green region. But here's another example, simple example. Now the region is a triangle. F of x is x, and a equals 0 and b equals 2 again. And the area is 2, but the surface area for a cone is pi r l, where l is the lateral length, the diagonal shown there on the diagram. And so that's pi times 2, which is the radius of the bottom of the cone, times l, which by the Pythagorean theorem is root 8. So now we've got 4 pi root 2, which does not equal 2 pi times the area anymore. The area stayed the same, the surface area changed. Now here's a more extreme example. If we had an area something like that, with a curve that goes up and down, and revolve that, then the area is still 2. We could make the area 2, but clearly the surface area is much greater than either of the other two examples. The curve, not the area of the region, produces a surface area. And so we have to do things a little bit differently. So let's look at our other example again. Here's our curve rotated around the x-axis. So instead of having delta x, we're going to draw diagonal lines and make a paper strip that on the right has a slightly bigger circumference than on the left in this particular example. And so instead of delta x, we have to use delta s. These paper strips would be an excellent approximation, and they would approach the actual surface area. So the area of this strip would be approximately the average between the two circumferences, the smaller one on the left and the larger one on the right. Take that average and multiply by the width of the strip, delta s, and that would be the area approximately. And so we can rewrite each circumference as 2 pi r1 and 2 pi r2, and then factor out the 2 pi. Now delta S can be written in terms of delta y and delta x using the Pythagorean theorem. So delta S is the square root of delta x squared plus delta y squared, which means the instantaneous change ds is the square root of the instantaneous change dx squared plus dy squared. Now if we want to integrate along the x-axis, we can factor out a dx, and if we want to integrate along the y-axis for some reason, we would factor out the dy. And so ds can be written either of these ways, depending on which axis we're going to have numbers and information about. Now, what about the r1 plus r2? As we make delta S shrink, then r1 and r2 approach each other and meet sort of in the middle at just r, every r. So you've got 2r divided by 2. And so that average morphs into just every r. And so our integral, our standard integral for surface area, is the integral from a to b, 2 pi r, which is the circumference, times the instantaneous change ds along the curve. In this case, if we rotate around the x-axis, the radius is f of x. That won't always be the case, but it is in this example. So there's our standard integral for surface area. If we rotate around the x-axis, it's going to look like that. And if we rotate around the y-axis, then the radius would be x rather than y, and we would run everything in terms of y. Another way to look at this is you could take those circles that go around the surface and straighten them out. And so we're sort of adding up these lengths, these line segments along the curve to get our surface area. So now we're going to look at an example from your text, Edwards and Penny. Y equals x squared for x between 0 and 4, and we're going to rotate around the y-axis. So there's our curve. There's our faux curve on the other side of the y-axis, and there's a typical circle. Notice that the radius is x. Now if we straighten that circle out, we can think of it as a line segment. The circumference is a line segment. Let's look at that again. Going along the curve, and we could integrate along the x-axis from 0 to 4, or we could integrate along the y-axis from 0 to 16. So there's the circle back. Let's start with going along the y-axis. So there's our integral from 0 to 16, 2 pi times the radius, which is g of y or x, and then there's ds in terms of y. And so solving for x, we can see that if y is x squared, x is the square root of y. And so the radius in terms of y is root y, and dx dy is the derivative of the square root of y, which is a half y to the negative 1/2. And if we simplify that, we get this integral, which I don't think you'd be able to integrate. I'm not sure offhand how we would integrate that. So let's take a look at the other option. If we integrate along the x-axis, then we have 2 pi r, and r is just x. And we have under the square root 1 plus dy dx squared, and dy dx is just 2x. That integral you could probably do with use substitution, but don't feel that you have to. If you wish, you can just use your calculator to approximate these integrals. So there's the final approximate answer. Okay, now let's look at another example. Same curve, different values for x, 0 to 1 this time, and we're going to rotate around the line y equals 4, not the x or y axis. So there's our curve and our line of rotation. There's our faux curve on the other side of y equals 4. There's a typical circle. Now this time the radius is not x or y. It goes from the line y equals 4 down to the curve. So it doesn't go all the way down to the x-axis, and therefore the radius is 4 minus y, or if we want it in terms of x, 4 minus x squared. So again, you can think of the straightening out the circles and making them into line segments, and then adding those line segments up along the curve, And let's look at that again. You could either add from 0 to 1 along the y-axis or 0 to 1 along the x-axis. There's the circle back. So there's our integral if we want to use the x-axis, 2 pi r ds from 0 to 1. And if we're doing it in terms of x, then the radius has to be 4 minus x squared. And dy dx is the derivative of x squared, which is 2x. And there it is simplified. Now that integral maybe you could do by hand if you split it into 2 and use trig substitution twice. Let's not. There's the approximation from the calculator. Okay, now let's do the same problem, only integrate along the y-axis. So this time, there's your integral in terms of y, 2 pi r ds in terms of y. R has to be, let me do a little preliminary work there. If y is x squared, then x is the square root of y, and dx dy is 1/2 y to the negative 1/2. So we rewrite the radius in terms of y, 4 minus y. We substitute our dx dy and square it. There it is simplified. And that one I'm not sure how you would do that by hand. Good luck with that. Instead, we'll just use our calculator to approximate it. Okay, so now it's your turn to try a few problems in section 6.4. Have fun.